Hello everyone. Today we will discuss about transmission of random process through a linear time invariant system. Consider an LTI system with impulse response HT. So this is an LTI system with impulse response HT. Assume that let XT be the random process given as input to this LTI system. And let YT be the random process obtained at the output of the LTI system in response to the given input XT. Now, what is the relation between XT and YT? YT equal to XT convolution HT. So, again, YT can be written as integral minus infinity to plus infinity x tau HT minus tau d tau, or integral minus infinity plus infinity h tau xt minus tau d tau. Assume that the statistical characterization of input random process is known. That is, we know the mean and autocorrelation of input random process xt. Now we need to find the mean and autocorrelation of output random process. How will you find the mean of the output random process? That is, we need to find mu yt. Now what is mu yt? Mu yt can be written as expectation of yt. Right. So this can be written as expectation of what is yt? Yt is integral minus infinity to plus infinity h tau xt minus tau d tau. Integral minus infinity to plus infinity h tau xt minus tau d tau. Now we are going to interchange the order of expectation and integration. So this can be written as integral minus infinity to plus infinity h tau into expectation of xt minus tau d tau. Right. So assume that the input random process xt is White's and stationary. So we know that if xt is White's and stationary, what happens to the mean? Mean will be, that is mu xt can be written as mu of x, which is a constant. Right. This we already discussed in the previous class. So equation number 1 gives mu yt can be written as integral minus infinity plus infinity h tau into what is expectation of xt minus tau. Expectation of xt minus tau is mu. So this we know that mu xt minus tau. Right. So we know that if the input random process is WSS, mu xt minus tau can be written as mu y, which is a constant, right? So this can be written as minus infinity plus infinity h tau into mu x d tau. Right. So this can be written as mu x into integral minus infinity plus infinity h tau d tau. So what is integral minus infinity plus infinity h tau d tau? We know that the frequency response of the system h of f can be written as integral minus infinity plus infinity h tau e raised to minus j 2 pi f tau d tau. Right. So what happens if f equal to 0? That is, what is h of 0? H of 0 can be written as integral minus infinity plus infinity h tau e raised to minus j 2 pi into 0 into tau. That is, e raised to minus 0 or e raised to 0 is 1. So this will be equal to integral minus infinity plus infinity h tau d tau. So we can see that this will be h of 0. What is h of 0? H of 0 we'll call it as DC response of the system. So that is mu yt. So mu yt equal to mu y equal to mu x into h of 0. Now what about h? Now where h of 0 is equal to mu y by mu x. which is this DC response of the system. Thus, mean of the random process yt produced at the output of LTI system in response to xt acting as the input random process is equal to the mean of xt multiplied by the DC response of the system. Now we need to find the autocorrelation function for output random process. How will you define the autocorrelation function? We know that Ry, I am considering two time, Rytu can be written as expectation of Yt into Yu. Right. So this can be written as expectation of what is Yt. Since we are considering two times t and u, we are writing Yt as integral minus infinity plus infinity h tau 1 x t minus tau 1 d tau 1 into integral minus infinity plus infinity h tau 2 into x u minus tau 2 d tau 2. So again we are going to interchanging the order of integration and expectation. This can be written as integral minus infinity plus infinity h tau 1 d tau 1. Actually d tau 1 and d tau 2 will come at the last. Anyway, I am writing here itself into integral minus infinity plus infinity h tau 2 d tau 2 into expectation of x t minus tau 1 into x u minus tau 2. Actually it will the d tau 1 and d tau 2 will come here itself. Okay, anyway, for the convenience I am write like this. So this is equation number 2. Okay, equation 2 can be written as, so what is this quantity? This is actually autocorrelation, right? So if the input random process is given as a Whiteson stationary random process, we know that autocorrelation function depends only on the difference between the observation time. So what is the observation time here? T minus tau 1 and u minus tau 2. Now the difference between the observation time will be T minus tau 1 minus u minus tau 2. That is, this can be written as T minus u minus tau 1 plus tau 2. Now let tau equal to T minus u. Now we know that, so if the given random process is WSS, autocorrelation function depends only on the difference between the observation time. So RYTU is RYT minus u. If YT is also WSS, which is equal to RY tau, where tau is T minus u. This will be equal to integral minus infinity plus infinity h tau 1 d tau 1 integral minus infinity plus infinity h tau 2 d tau 2. Now what about this quantity? This quantity will be Rx tau minus tau 1 plus tau 2. Now I am going to write this particular equation, that is equation number 3, in a systematic way. That is, this is actually correct. Ry tau can be written as integral minus infinity plus infinity, again integral minus infinity plus infinity, h tau 1, h tau 2, Rx tau minus tau 1 plus tau 2, d tau 1, d tau 2. So this is actually correct. So this is equation number 4. By property number 1 of autocorrelation function, we know that autocorrelation function evaluated at tau equal to 0, that is Rx of or Ry of 0 is the average normalized power in the random process Yt. Or simply we can say that it is the mean square value of the output random process. Now the mean square value of output random process, that is expectation of y square t will be equal to ry0. Now mean square value of output random process can be, so in equation number 4, just put tau equal to 0. So this will be equal to integral minus infinity plus infinity minus infinity plus infinity h tau 1 h tau 2 rx tau 2 minus tau 1 d tau 1 d tau 2. So this is mean square value of output random process. This is equation number 5.